So there is something called simplicial complex. Let's say we have some vertices. So these are some vertices, and let's say this vertex is v1, this vertex is v2, v3, and v4. So you can assume these vertices can be in some three-dimensional space or some two-dimensional space. It can be any RD. Let's say it's general RD space. So D can be 2, 3, or 4, anything, right? So these are some vertices in some real space, and let's say V, capital V, is a set which is of these vertices. Okay, so capital V is a set of these vertices v1, v2, v3, and v4. Okay, so what is simplicial complex? Simplicial complex, first of all, it is denoted by k. So k is the letter we have chosen to denote simplicial complex. So when I say k, I am saying I'm talking about simplicial complex. So what exactly is k? K is, first of all, it is a it's a power set, or I can say superset. And superset of what? Uh, all the subsets of V comes in this uh, K. K, which is a power set of subsets of V. So in K, we have all subsets of this set V, except the null set, so K can't be empty. So people can say K is family of those uh, subsets. So in fact, it is not necessary that we have all subsets. We can have some subsets only. But this is not a complete definition of K. One more thing, there are two conditions. First of all, in K, we must have all the singleton sets, singleton subsets. Okay, so K is defined over V. So first of all, let's see what are all the possible subsets of V. So um, if we draw the subsets of set V, which is a set of vertices. So what are the possible subsets of V? First of all the singleton sets. So V1, then V2, V3, then V4, right? And then we will have such sets of two element. So we will have V2, V1, V2, and V1, V3, right? And what else? V1, V4, and we'll have V2, V3, will have v2 v4, and we also have v3 v4, right? v1 v2 v1 v3 v1 v4 v2 v3 v2 v4 and v3 v4. Okay, so these are the possible subsets of two elements. Similarly, we'll have subsets which have three elements. So one can be v1 v2, and then I can add v3, right? And another subset can be v1 v2, and I can add v4, and we can have v1 v3, I can add v4 to it. So 1 3 4 haven't covered yet. So, and we can have v1, so v1 v2 v1 v3 v2 is already covered. So another set can be v2 v3, and I can add, so v1 is already covered, 2 3 v4. So this can be, so 2 3 4 is not covered yet, right? And v2 2 4 1 is covered, 2 4 3 is covered, 3 4 1 is covered, 3 4 2 is covered. So yeah, these are the sets of element which have three elements. And last possible set is which have all these vertices, v1 v2 v3 and v4. So these are the all possible subsets. These are all possible subsets of subsets on of vertex v, right? So if I want to make a simplicial complex on v, let's make a simplicial complex on v. Let's make a simplicial complex k on set of vertices v. So since k is a power set, it will have all these subsets as their element. So you can choose any of the any of these sort sets to include in your k, but you must include the singletons first. So what are those singleton sets? These v1 v2 v3 v4, they must belong to k. If they are not in my set, then that's not a simplicial complex. You can't just have these 2 degree sets and you don't have any singleton set in there. So singleton set must be in my simplicial complex. So at bare minimum, condition is that these singleton sets v1 v2 v3 and v4 must be there. So is it a simplicial complex? Yes, it is a simplicial complex. If I do just this, then it is a simplicial complex. And if I want, I can add some other element also. So let's choose this set to include in my simplicial complex. So let's include it. So I have included v1, v2 and v4, this subset as my element of this simplicial complex. So whenever I include a set in my simplicial complex, first of all, it should have all the singletons. So first condition is we have singletons. So we have covered singleton sets. Second is that for any set which is belonging to k, any set, let's say sigma, is a set is a subset of is an element of K, I should say sigma belongs to K. So any element which is of course a set which belongs to K, all subsets tau of sigma must also belong to K. What I'm saying is that if you have included this set v1, v2, v4, then its smaller versions, its subsets should also be present. And what are the subsets of this set? These are v1, v2, v1, v4, and v2, v4. So I must include them also in my complex. So whenever you include this, you have to include this also, v1, v2, v1, v4, and v2, v4, right? So when I included this set, it was my compulsion to include these also. So now it's a simplicial complex, another simplicial complex. So whenever you are including any set to my simplicial complex, its smaller version should also be present there. Its subset should also be present there. So in general, how we write this as mathematically? If I mathematically write it, a simplicial complex K defined on V is a vertex of V, have these conditions. First condition, all singleton subsets of V must be included. That's the minimum condition which should be satisfied. Must be included in K. And for any sigma which is a set which belongs to K, there should be all tau which are subsets of sigma. This tau should also belong to K, right? If this is true, then for all tau, for all subsets of the sigma, those subsets should also belong to K. So this is what we can mathematically formulate whatever we did above. And also, usually people in TDA, people in topology, while writing this simplicial complex, although the elements are sets only, the elements of this simplicial complex are sets only, but to avoid the just for the simplicity, people just avoid these curly braces. People avoid these curly braces, and usually to save time or for the simplicity, people write this simplicial complex like this. So they just simply write it K equals to V1, V2, V3, V4, then V1, V2, V4 is just simply write it as V1, V2, and V4. So they just concatenated all these vertices without any comma. This V1, V2, V4 is nothing but it is same thing that if you write it like this, V1, V2, V4 in a set can be written like this, V1, V2, V4, right? And similarly for V1, V2, they'll just write V1, V2, V1, V4, and V2, V4. So this is one way of writing this same simplicial complex. This can be written like this also. So it has all the singleton sets V1, V2, V3, V4, and since I included V1, V2, V4, I had to include V1, V2, V1, V4, and V2, V4. So if you are including a set of element 3, then you should include its subsets which are of element 2 and 1. Single sets are always there, right? Great. So now we know what simplicial complex is, but if I tell you how actually we visualize this simplicial complex, for that, since we have drawn these vertices v1, v v1, v2, v3, and v4. So this was v1, v2, v3, v4. If I want to draw this, so now right now we are drawing simplicial complex. Simplicial complex K. So I am drawing this simplicial complex. This v1 singleton set v1 represents a single dot. So single dot represent a singleton set. Similarly, this single dot represent this singleton set v2. This v3 singleton v2, v3, and v4. How do I visualize this? These let's start with v1, v2. How do I draw this v1, v2? So to show that this v1, v2 is set of v1 comma v2 is present, I'll just draw a edge between v1 and v2. So this edge represents v1, v2. So v1, v2 is present. Similarly, this edge represents v1, v4. And we have v2, v4 as well. So this edge represents v2, v4. And since we don't have v1, v3, so I will not draw the edge between v1 and v3. Again, we have v1, v2, and v4. So how do you represent that in your diagram of simplicial complex? So v1, v2, and v4, that will be represented by the filling of this triangle v1, v2, v4. This is the triangle v1, v2, and v4. This is the triangle, right? So if I fill this triangle, so this plane is filled, we don't have any hole in it. This filling represents v1, v2, v4. So v1, v2, v4 is filling of triangle v1, v2, v4. So triangle constructed through vertex v1, v2, and v4. This filling, the filling inside this triangle is when the triangle is empty, it is not filled. Then this shows that v1, v2, v4 is absent. But when I fill this triangle, then this means v1, v2, v4 are present. Right? So this is the visual representation of this simplicial complex. So yeah, so now you know what is simplicial complex. Simplicial complex is nothing but is a power set which is defined over some vertices, and we know how to visualize the edge or the dot and the triangle in our simplicial complex. Now there is called something called dimension of your simplicial complex. There's something called dimension of simplicial complex. Before that, all these entries, all these elements that belongs to K, this v1, this v2, this v3, v4, and then this v1, v2, v4 is a single entity. Then v1, v2, v1 is a single entity. This v1, v4 is a single entity, and this v2, v4 is also a single entity. These single entity are called simplex. So these are called simplex. and simplex is a singular word, and as a whole I can say that these are nothing but simplices. So v1, v2, v3, v4, all these elements are called simplices. So elements of K are called simplices. So one statement I'll make here, elements of K are simplices, right? So simplex is the singular word for these elements, and simplices is the plural word. So I can also say that complex, or I should say simplicial complex. Sometimes people just say complex instead of simplicial complex, but let's try it simplicial complex. This simplicial complex is made up of simplices, right? And how do we define the dimension of this simplicial complex? How of what dimension this simplicial complex is? So first of all, uh, we can find the dimension of particular simplex. So dimension of, if I tell you what is the dimension of this simplex, to find the dimension of any simplex, so let's say sigma is a simplex, then dimension of sigma is nothing but cardinality of sigma minus 1. Cardinality means the number of elements in that set. So if you have 5 elements in your set, then 4 is the dimension. If you have 3, then 2 is the dimension. So if I ask you, what is the dimension of this simplex? 2, right? Because 3 elements are there in this set. So dimension of this simplex is 2. Similarly, what is the dimension of this simplex? It's 1. And what is the dimension of this simplex? It's 0, because it has only single element in this set. And what is the dimension of this whole simplex? That is the maximum dimension that we can have in this entire simplex. So one by one, for all simplexes, dimension of this simplicial complex is maximum of dimension of sigma for all sigma that belongs to K. So take every simplex from your simplicial complex, find its dimension, and keep on checking all the dimension. Whichever is the maximum, that will become your dimension of simplicial complex. So now you know what is simplicial complex. You can visualize your simplicial complex. You know what is a simplex, which simplex are nothing but foundational unit of simplicial complex. And you know how to find the degree of dimension of simplex. You know how to find the dimension of a simplicial complex. Great. Now so if I just draw a diagram and I'll say that this is V1. What is the degree of this? So this is a simplicial complex, right? It just has only one vertex, and its simplicial complex K will have only the singleton set V1, right? Because no more subsets are possible in this set of vertices. So what is the degree of this simplicial complex? Dimension. So dimension will be 0, right? Let's say I give you another simplicial complex. This is something like this. So this is edge. This vertex is v1. This vertex is v2. Since edge is present, it means v1 v2 is also present. So what is the degree dimension of this simplicial complex? So dimension of this v1 simplex is 0. This v2 simplex is 0. But dimension of this v1 v2 simplex is 1. So maximum is 1. So a dimension of this simplicial complex is 1. If I show you this, v1, v2 and v3. Now tell me what is the dimension of this simplicial complex. So since we have a dot here, dot means singleton set v1, it has a dimension 0. This dot has dimension 0. This dot has dimension 0. And since this edge is present, which means v1 and v2 is also present. And dimension of this v1, v2 is 1. Again, this edge is present, which means v1 and v3 is present. And dimension of this simplex is 1. v2, v3 is present. Dimension of this complex is 1. And this triangle is not filled. There is no filling inside this triangle. This triangle is empty inside. So there's a hole. There's a transparency between inside this triangle. So v1, v2, v3 is not present here, right? So you can't say that there is another simplex v1, v2, v3. So what is the dimension of this simplicial complex? The maximum we got is 1. So again dimension is 1 here. Dimension is 1. Another example. So this is another simplicial complex, v1, v2 and v3. I have an edge here, edge here, edge here, and this time this triangle is filled. It is not empty inside. This triangle is filled. So tell me what is the dimension of this simplicial complex. So this dot have dimension 0. This dot has dimension 0. This dot has dimension 0. This edge has dimension 1. This edge has dimension 1. This edge has dimension 1. But since this triangle is filled inside, so which means v1, v2 and v3, this entity is also present in the simplicial complex. And the dimension, this is nothing but cardinality minus 1. So 3 minus 1 is 2. So dimension of this is 2. So what will be the dimension of this entire simplicial complex? That will be 2. Great. So now I have given you some examples also, through which now you can practice on your own also by drawing some simplicial complexes and guess what its dimension is. But that's pretty easy, right? It's very easy to get the dimension of your simplicial complex. Great. Now we'll talk about something called phase. Let's say you have two simplexes, sigma and tau. Sigma also belong to K, tau also belong to K. And this sigma is a subset of tau, right? This sigma can be exactly equal to tau, or sigma can be some smaller version of tau, right? Tau is a simplex. Tau is a simplex, and sigma is also simplex, and sigma is a subset of tau. Then this sigma can be called as phase of tau. What is an example? So one simplex I'll give you is v1, v2 and v3, and you know what it is. It is a set of v1 comma v2 comma v3. So let's say this is tau, right? And another set v1 v2, which is sigma. So this sigma, is it a subset of this tau? Right, it is a subset of this tau. v1 comma v2 is included in this tau. So which means I can say that v1 v2 is a phase of v1 v2 v3. And how can I draw it visually? What is this? This is nothing but edge between v1 v2. And how can I draw this? It is a filled triangle. So from this I can say that edge is a face of triangle, right? So for this filled triangle, this is its face, this is also a face, this is also a face. Also v1 v2 v3, I didn't say that it's a proper set. Its sigma can be equal to tau, right? So v1 v2 v3 itself can be a face of itself, right? So it can be a smaller version or can be just equal. It's just that we need a subset of that simplex. So all the subsets are face of that simplex. Now we will talk about some special kind of simplexes. K-simplex, special kind of simplicial complexes. So k-simplex. So k-simplex, so it is a small k, it's not big k. K-simplex. What is k-simplex? Point number 1. K-simplex, it is a simplicial complex. It is a simplicial complex. Simplicial complex. Okay. K-simplex is not a simplex actually. It is a simplicial complex which has some simplexes inside it, right? And k-simplex is defined on which vertex set? So vertex set is defined on vertex set, vertex, or I should say vertices set this. So there are two types of. So just say assume that there is some vertex at V. I'll tell you what is a V, which vertices we have in this V. So this k-simplex is also of two types. One is solid k-simplex, another is hollow k-simplex. So the difference between solid k-simplex and hollow k-simplex is just a small difference between their set V, set of vertices on which they are defined. In solid k-simplexes, vertex B starts from 0, 1, 2, 3, so on to whatever is the value of k. In hollow simplex, so in general I can say that k is greater than equal to 0, right? In hollow k-simplex, vertex is vertex set start from 1, then 2, then 3, so on to k. So in this case I can say that k is greater than equal to 1. Great. So vertex set of solid k-simplex is starting from 0 then all the way to k. And in hollow k-simplex, the vertex set start from 1 and all the way till k. It will make sense when I give you example of these solid and hollow k-simplex. So let's draw 0 simplex. So when k is 0, when k is 0, when k is 0, what will be the vertices in V, set V? That will be 0 only, right? In V will have 0 only, right? So the simplicial complex that will define on k is equal to 0 will have the set 0 only. So this single dot is k simplex, 0 simplex. Now let's draw solid 1 simplex. That means k is equal to 1. What will be the elements in your set? In vertex set we have 0 and 1, and this k simplex will have all the possible subsets. Above I told you that in simplicial complex we can have subsets of our choice depending upon the condition that it has all singleton sets, and whatever the set I'm including in it, its smaller version, its subset should be therein. But in this k simplex I need all the possible subsets. So what are all possible subsets of 0, 1? 0 should be there, 1 should be there, 0, 1 should be there. What else? This is all we have, right? So this is small k. So its simplicial complex k will be 0, 1 and 0, 1, right? And how can I draw it visually? I have a single dot for this 0, I have a single dot for this 1, and for this 0, 1 I'll draw an edge. So this is one simplex. And what will be similarly, what will be a solid 2 simplex? So we'll have 0, 1 and 2 in my set of vertices. And what are the all possible subsets? 0, 1, 2, then 0, 1, 0, 2 and 1, 2, and also 0, 1, 2, right? So let's draw its solid k-simplex. It will be something like that. We have this dot for 0, dot for 1, dot for 2, we have the 0, 1, we have 0, 2 and we have 1, 2, and also we have 0, 1, 2. That means this triangle is filled. This is solid 2 simplex. So k is 0, 1, 2, 0, 1, 0, 2, 1, 2 and 0, 1, 2. So 0, 1, 2 is nothing but filling of this triangle. Great. Now let's see what is hollow simplexes. In case of hollow simplexes, we don't have k is equal to 0. K is equal to 0 is not possible. So 0 simplex is not possible in hollow k simplex. Hollow k simplex start with 1 simplex. So 0 simplex not valid, not valid in holo. So holo zero simplex does not exist, does not exist. DNE does not exist. Holo zero simplex does not exist. Solid zero complex is just a dot. So what will be uh, holo one simplex? Holo one simplex. What will be my holo one simplex? So first of all, it is defined on what will be the vertex set? Vertex set will be having single element one only, right? Okay, I did one mistake. In holo simplex also, we include 0, but we in your holo simplex, what we exclude, will exclude the since we have all the subsets in our in your simplex, we exclude the subset from 0 to 1 till k. The subset having all the elements, we exclude that. So k is greater than equal to 1. That's right. Holo zero simplex is not defined. That's right. Holo zero simplex is not defined. That's right. But when we include the subsets in our simplicial complexes, we don't include the set which includes all the elements. So um, when we have vertex set 0, 1, and 2 and 3. So this is for k is equal to 3. So in case of solid k simplex, 0, 1, 2, 3 is included. But in case of solid case, in case of solid, it is included. 0, 1, 2, 3 is included. But in case of holo simplexes, 0, 1, 2, 3 is not included. So to draw, if to do some less work, let us include 0, 1, 2 only. So for 0, 1, 2, what are the possible all subsets? 0 subset, 1 subset, 2 subset, 0, 1, 0, 2, and 1, 2, and again I'll also include 0, 1, 2. But here in holo simplex, holo k simplex, we will include 0, we will include 1, we will include 2, we will include 0, 1, we will include 0, 2, we will include 1, 2, but we do not include 0, 1, 2. The set which is having all the elements of this V will not be included in holo simplex, holo k simplex, right? So it's a proper set. Set of proper sets is the holo k simplex, and set of all proper as improper sets, that is solid k simplex. So in solid k simplex, we have all the sets, all the subsets, whether it's the set V itself. But in holo k simplex, we don't include the set having all the vertices at once, right? So in case of holo one simplex, the vertex set will be 0, 1 also. So here also we have the vertex set 0, 1, and here also we have 0, 1, but its simplicial complex will be 0, 1, but not this 0, 1. 0, 1 is not included here. So it is the holo k simplex. So how will you draw its diagram? So for 0, I have a dot. For 1, I have a dot. And this edge is not present. So this is my solid one simplex, and this is my hollow one simplex. Are you getting what is the difference between both of them? The element having all the elements is not the subsets having all the elements is not included in hollow simplex, but it is included in solid simplex. So if I tell you draw the uh, hollow two simplex, how will you draw it? Hollow two simplex. So again you have the vertex. So I told you wrong there that 0 is not included. 0 is included. So the vertex set that we use is same in both k-simplexes. The only difference is that in solid k-simplex we include all the possible subsets. In hollow k-simplex we include all possible except the one having all the elements at once. So vertex set is same here, 0, 1 and 2, but if I say I tell you that what will be the solid simplicial complex on this V, that will be 0, 1, 2, 0, 1, 0, 2, 1, 2, but 0, 1, 2 is not present here, right? So single dot for 0, single dot for 1, single dot for 2, 0, 1, this edge, 0, 2, this edge, 1, 2, this edge. And since 0, 1, 2 is absent here, so this triangle is not filled, is empty inside. So this is my hollow two simplex. So you can see visually also this triangle is filled inside, so it's a solid simplex, and this triangle is empty from inside, so this is a hollow simplex, right? Again for k is equal to 3, for k equal to 3, k equal to 3, what will the vertex set? Vertex set will be 0, 1, 2 and 3. Let's make their hollow simplex and solid simplex. So here I'll define the solid k simplex. So it will have 0, 1, 2, 3. It will have 0, 1, 0, 2, 0, 3, and it will have 1, 2, 1, 3. What else? 0, 1, 0, 2, 3, 1, 2, 1, 3, and 2, 3. And also it will have 0, 1, 2, 3 simultaneously. And for hollow, this one is solid and this one is hollow. So in hollow 3 simplex, again I have 0, I have 2, 1, 2 and 3. I will have 0, 1, 0, 2, 0, 3, 1, 2, 1, 3, 2, 3, but I won't have 0, 1, 2, 3. Right? So if we draw this visually, we have some vertex here, v1, 0, 1. So let's say this is 0, this is 1, this is 2, and this is 3. So all those singleton sets are present. This 0, 1 edge is present, 0, 2 edge is present, this 0, 3 edge is also present, the edge between this 1, 2 is present, the edge between 1, 3 is also present, and the edge between 2, 3 is also present. So you can visualize it. It's a tetrahedron, right? Tetrahedron. And also I missed those three subsets. So it also has 0, 1, 3. So this face is filled and this face is also filled. So I don't know how to draw it on paper because it's hard to visualize, right? So 0, 1, 3 is also present here, and 0, 2, 3 is also present here, and 1, 2, 3 is also present here, and 2, 3. So 0, 1, 3, 0, 2, 3, 1, 2, 3, and 0, 1, 2. So these subsets of having three vertex. So these all the faces are filled. So faces are filled. Faces are filled. Faces of tetrahedron is filled. And what will be the tetrahedron of hollow k-simplex? Faces are filled, and also the solid tetrahedron, it is filled inside. So this solid tetrahedron is 0, 1, 2, 3. What it will represent? It will represent the filling inside this tetrahedron, not the filling inside triangles. So faces are filled. So this 0, these three simplexes of dimension 2 represent that these faces are filled, but inside that triangle there is no empty space. From inside, this tetrahedron is filled. It is solid. There is no empty space inside this tetrahedron. But in case of this hollow k-simplex, how should I draw it? So in case of this hollow, faces are filled, but the tetrahedron is empty inside. There is empty space. It's like the pyramid is empty from it. You can enter inside the pyramid. But in case of solid tetrahedron, it is not empty. It is filled. You can't enter inside the tetrahedron. You can't enter inside the tetrahedron. But in case of hollow tetrahedron, hollow 3 simplex is nothing but a hollow pyramid or a hollow tetrahedron, and solid 3 complex is a solid tetrahedron. So here faces are filled. Again, they are 0, 1, 3 and 0, 2, 3 and 1, 2, 3 and 0, 1, 2 are present in this family of sets. But 0, 1, 2, 3 as a whole is not present. So 0, 1, 2, 3 is what? 0, 1, 2, 3 is the filling of tetrahedron. Okay, so 0, 1, 2 is filling of tetrahedron, which is present in this solid 3 simplex, but is absent in hollow 3 simplex. So if you want to draw k equal to 4, you can try, but it's hard to visualize. It already became difficult when we try to visualize this 3 simplex. So 4 simplex, 5 simplex, 6 simplex, it's difficult for humans to visualize. So that's all in this video. Now you know what is simplicial complex, what is a simplex, what is a face of a simplex, what is the degree of a simplex, and what is the overall degree of a simplicial complex. How can you visualize these simplicial complexes? How can you represent the edge? How can you write a simplicial complex just mathematically, algebraically? Just write a set of k, family of sets, and how you can convert that set family of k into a visual diagram. And you got to know what are solid k, what is k simplex. So k simplex is something whose vertex set is from 0 to k. So in both solid k simplex and hollow k simplex, you have vertices from 0 to k. But in solid k simplex, we also include the subsets. So we include all the possible subsets. In solid k simplex, you include the subset having all the elements at once. But in hollow k simplex, you don't include that set which have all the elements at once. So you got to know about k simplex, solid k simplex, and hollow k simplex.